Hi, my name is Laura Burdick, and I am pleased to present my work on analyzing the surprising variability in word embedding stability across languages. So, breaking that down, this work is really looking at word embedding stability, and we're looking at it with a bunch of different languages. So, before we dive in, let's talk a little bit about what is stability. So, stability in the context of word embeddings is defined as the percent overlap between 10 nearest neighbors in an embedding space. So let's suppose we have this embedding space and we care about the word international. And here are the words that international is surrounded with. And let's say we have another embedding space and we care, these are the 10 words around international in our second embedding space. And maybe these two embedding spaces use different algorithms, maybe they use different data, maybe they even just use a different random seed and they use the same algorithm and the same data. If we want to measure the stability of the word international across these two embedding spaces, we're going to look at the 10 nearest neighbors in each space and we're going to count how many of those nearest neighbors are the same. So in this case, 4 of the 10 nearest neighbors are going to be the same across these two embedding spaces. So we're going to say that international has a stability of 40% across these two embedding spaces. So this idea of stability kind of captures the concept of like, do the two embedding algorithms kind of produce the same sort of space? Are the nearest neighbors approximately the same for a given word? Okay, so in this particular work, we're going to ask two main questions. The first question is, does stability vary for different languages? So previous work has already looked at word embedding stability in English, but there's been no previous work that has looked at word embedding stability in other languages. So in this work, we're going to ask, is stability the same for all of these different languages? And also, if we see differences in stability between different languages, which, spoiler, we do, is this stability associated with linguistic properties? Are certain linguistic properties associated with higher stability or lower stability? So in order to investigate these questions, we're going to consider 3 different sources of data. Our first is Wikipedia. We have Wikipedia dumps in 40 languages. Our second is the Bible. We have the Bible corpus in 97 different languages. And then for our linguistic properties, we're using WALS, which is the World Atlas of Language Structures. And it includes phonological, lexical, grammatical properties for over 2,000 languages. So that's where we get our linguistic information from. We're going to run 2 major experiments in this paper. The first is comparing the stability of embeddings for 26 different languages. So we're going to do this across both Wikipedia and the Bible, and we're going to kind of compare stability across these 2 different corpuses. So the first is Wikipedia, and we're going to look at 3 different settings for stability in Wikipedia. The first is using glove embeddings, and we're going to create 5 downsampled corpora, and then for all the words in common across those 5 downsampled corpora, we'll create glove embeddings, and then we can calculate the stability across all 5 corpora. In the example I showed you earlier, we just calculated stability across 2 embedding spaces. You can extrapolate that definition to as many embedding spaces as you want. So here we're going to calculate stability across 5 spaces for all the words in common across those spaces. Okay, second, we're going to look at word-to-vec embeddings across 5 downsampled corpora. So same as the first, different algorithm, word-to-vec. And then third, we're going to look at word-to-vec embeddings using 5 random seeds on 1 downsampled corpus. So we've got 1 corpus, and then we run word-to-vec 5 different times on that 1 corpus using different random seeds. So word-to-vec has randomization in it, so you can set the random seed to be different, and you're actually going to get different results if you set a different random seed for word-to-vec. So those are the 3 settings we consider for Wikipedia. A quick note, a question that comes up about this work is, why are we using glove and word-to-vec? Why are we not using more modern embedding algorithms like BERT or ELMO or some of those? And I'll say to that glove and word-to-vec are still really commonly used algorithms, particularly in areas like the computational humanities and areas with low resource languages. So research into them is still a valuable thing. Okay, we're also going to look at the Bible. Now the Bible is a lot smaller than Wikipedia, so we're only going to do 1 setting here, and we're going to do the last setting, stability of word-to-vec embeddings using 5 random seeds on 1 downsampled corpus. And the reason we only do this setting is the Bible is just too small to have 5 downsampled corpora. Each downsampled corpora is going to be 100,000 sentences across all of these, and we're going to be looking at 26 different languages. So, to take an example of what these results look like, I have full results for all 26 languages in the paper, so check that out. Here's an example for English. So you can see that there are 4 different lines on this graph. There's a green, dotted green, pink, dotted pink. Those are the different settings. So the dark green is the Bible, and then the other lines are the 3 different settings that we talked about with Wikipedia that are listed on the last slide. You can see across the y-axis here, this is the percent of words that fall in a stability bucket. So all these words over on the left-hand side have really low stability. This is it's a log scale, but this is basically how many words fall in like the stability bucket between say 0 and 10% or 10 and 20%, and we go all the way from 0 to 100%. So you can see that a lot of the words are low stability, and then it kind of flattens out towards the middle, and then there's just a few words that have really high stability. So this is what this graph looks like for English. You can see these graphs in the paper for all 26 different languages. One of my takeaways from this experiment was that they actually all look pretty similar. They all follow pretty similar trends. There's a few languages that look a little bit different, but they all look pretty similar. So I'll point out 2 more languages while we're talking about these results, and that is going to be Vietnamese and Korean. So Vietnamese has the overall highest stability, and Korean has the overall lowest stability. So this shows you 2 patterns that are potentially a little bit different from some of the other languages in our experiment. Why does Vietnamese have the highest stability? We don't know for sure. One reason could be that it's the only family that we have from that language family. And so it could have different characteristics that are impacting its stability, and that's why we see a higher stability with Vietnamese than we see for other languages. Okay, the second experiment that we do is we want to understand this a little bit better. So the graphs are nice. It's nice to see these trends. It's nice to see high and low languages, but we really want to get at what is like related to stability in a language. So this is where we're going to use a regression model, and we're going to use our regression model to predict stability in a language using linguistic properties. So we're going to model this using ridge regression, and we're going to look at 37 different languages. The input to our regression model is all of those WALS properties. WALS, remember, is the kind of encyclopedia where we get all the linguistic information for the different languages. So we have 97 different WALS properties. The output is going to be the average stability of all the words in a language. And when we fit this model to our 37 languages, we get a really high R-squared score. So this is a model of fit of the regression model. We get a high R-squared score of 0.96. So we're confident that the model is learning something interesting about the relationship between WALS properties and stability. So here are 2 conclusions that we can pull out from our regression model. And the first conclusion is that more affixing, so affixing is suffixing, prefixing, is associated with lower stability. And this makes sense because if you have affixes, they increase word variation. If you take like the word walk, you have walk, walked, walking, walker. You have all of this word variation, so it makes sense that in languages where you have more of this affixing, you're going to have more word variation, and thus you're going to have lower embedding stability. So this is a box and whisker plot looking at one of the WALS properties related to affixing. There's a couple of different WALS properties related to it, and I've put them all in the paper. But this is looking at prefixing versus suffixing in inflectional languages, and then it's looking at the average stability down here on the bottom of the box and whisker plot. So you can see that languages that don't have a lot of affixing are going to have a higher stability, and languages that do have more suffixing are going to have a lower stability. The second result that we can take away from our regression model is that languages with no gender system are associated with higher stability. And again, this is intuitive. If you have a language that has a gender system, then there's going to be more word forms in that language. There's potentially going to be a male word form and a female word form of different common words. And so this is going to lead to lower stability that we see in the word embeddings. Again, here's one of the WALS properties displayed as a box and whisker plot. This is looking at the number of genders present in a language. And you can see we have a group of no genders, and then we have a group of 2 genders. And the other numbers aren't shown here because we didn't have enough languages to get good data on that. But you can see that the languages that have a no gender system are associated with a higher stability. So these are just 2 of the conclusions that we can draw from our regression model that help us understand a little bit better word embeddings in different languages. So some final thoughts. We saw languages with more affixing tend to have less stable embeddings. Languages with no gender systems tend to have more stable embeddings. And so what can we do with this? We can use these insights to inform future embedding design. Future embedding design needs to take into account gendered words and morphologically rich words with affixes. And so these are things to be thinking about as we design embeddings, not just in English, but in many different languages. You can download our code online. Thank you for your time.